Before the final scene, I want to reveal two important inequalities. Yes, one more mathematical result to know. They are the bridge between Morse theory and the deeper algebra hidden inside geometry, cohomology. First is the weak Morse inequality. For each index k, the number of critical points of index k is at least the kth Betti number. This inequality is easy to see with a torus and a potato. For a torus, a simple height function has 1 index 0, 2 index 1, and 1 index, 2 critical point exactly matching its Betti numbers. 1, 2, 1. For a potato, a height function might have 1 index 0, 1 index 1, and 2 index 2 critical points, larger than the sphere's Betti numbers, 1, 0, 1. Second is a stronger Morse inequality. If you take the alternating sum of critical points, it is at least the alternating sum of Betti numbers. So even after all possible cancellations, the remaining critical point data still cannot be smaller than what cohomology demands. The idea of the proof of the strong inequality is also surprisingly simple. From a Morse function, you can build a chain complex. We can keep the chain complex completely arbitrary here. What it really is doesn't matter yet, because it's not always easy to construct the geometric one when we need it. Ideally, we'd like to tie everything to de Rham cohomology, since that's what differential geometers and physicists are most familiar with, but we can't justify that link at this stage. So for now, we just take the proof as a purely algebraic statement about an arbitrary chain complex. Its generators are critical points. So, how many generators in degree k equals the number of index k critical points? And the homology of this complex matches the manifold's cohomology data. So, homology in degree k equals the Betti number. In each degree, the generators split into three parts. The part that is immediately a boundary, the part that represents real homology, and the part that will become a boundary 1 degree lower. So the number of generators equals Betti number plus some extra pieces plus extra pieces from the previous degree. Those extra pieces are always non-negative and they always come in adjacent degrees. When you take an alternating sum, these adjacent extra pieces cancel each other out except for one leftover non-negative chunk at the end. So the alternating sum of critical points cannot drop below the alternating sum of Betti numbers. That leftover chunk is exactly why the strong Morse inequality is always true.